Vector databases, the quiet engine behind almost every AI product you have used this year. Every time a chatbot answers from your company's documents, every time an app shows you more like this, every time an AI agent remembers something you told it last week, there's a good chance a vector database is doing the heavy lifting underneath. In the next few minutes, I'm going to show you exactly what they are, how they work, and how machines turn meaning into math, and then find it again in milliseconds. I'm Gurmeet Singh. Let's get into it. To understand why vector databases exist, we first have to understand what they fix. For decades, search worked by matching keywords. You type some words, the system looks for documents containing those exact words. Simple, and for a long time, good enough. But keyword search has a blind spot. It doesn't understand meaning. Say you search how to fix a car, a keyword system will completely miss a perfect article titled Automobile Repair Guide or another one called Vehicle Troubleshooting. Why? No shared words, so no result. Synonyms, context, intent, all of it is invisible to lexical matching. The new approach flips this on its head. Instead of matching letters, we match meaning. The system understands that car, automobile, and vehicle are basically the same idea. It works across different phrasing, even across languages. And this single shift, searching by meaning, is what powers modern chatbots, recommendation engines, and the whole world of AI search. So the big question is, how do you teach a computer what meaning actually is? The answer is a concept called embedding. And this is the core idea of entire video. So let's slow down here. An embedding turns meaning into numbers. Here's the flow. You take a piece of raw text, let's say the phrase a puppy playing in the park. You feed it through an embedding model, which is just a neural network trained on enormous amount of data. And out the other side, you get a vector, a long list of numbers, often hundreds, sometimes over 1,000 of them. A common size is 1500 and 36 dimensions. Now, three things to hold on to. First, each number is a coordinate, and a vector is really just a point in space. Except instead of three dimensions like the world around us, it lives in hundreds of thousands of dimensions. Second, direction encodes meaning. Things that mean similar things end up pointing in similar directions. The model learns this pattern from billions of examples. And third, it's like a fingerprint for meaning. And here's the beautiful part. It's not just the text, images, audio, video, anything can be embedded into the same comparable space. So if meaning becomes a point in space, then similar meanings become points that sit close together. Closeness in space equal closeness in meaning. Look at this picture. I have simplified it down to two dimensions so we can actually see it. But remember, real vectors have hundreds of dimensions. Notice how things naturally cluster. All the animals group together in one region. The vehicles form their own cluster. The food sits somewhere else entirely. The model was never told those categories. It learned them just from how the concepts relate. Now watch the white dot. That's our search query. To find the best matches, we simply look for the points nearest to it. Here's it sitting right inside the animals cluster. So those are our top results. But nearest needs a definition, and there are a few ways to measure distance. Cosine similarity compares the angle between two vectors. It's the go-to choice for text because it captures direction while ignoring length. Euclidean distance or L2 is just the straight line distance between 2 points, the intuitive one. And dot product is fast and popular when vectors are normalized. It quietly powers a huge number of production systems. Different metrics, same goal, measuring how close two meanings really are. Okay, so we can turn things into vectors and we can measure how close they are. Now we can finally define the star of the show. A vector database is a database purpose built to store, index, and query embeddings, finding the nearest vectors to your query by meaning at massive scale in milliseconds. The way it works come down to four-step pipeline. Step one, ingest. You take your data documents, images, audio, and you chunk it into manageable pieces. Step two, embed. Each chunk runs through an embedding model to become a vector. Step three, index. The vectors get stored in a special structure built for fast retrieval. We will talk about how that works in a moment. And step 4, query. When a question comes in, you embed it the same way and then fetch it nearest neighbors. Ingest, embed, index, query. That loop is the heartbeat of every vector database. Now you might be thinking, I already have a database. Why can't I just use SQL? It's a fair question, and the answer reveals why these systems are special. A traditional database is built for exact matches and ranges. Find me the row where the name equals Gurmeet. Its indexes, usually B trees, assumes your data can be stored on a key. That's perfect for names, dates, and IDs. But ask it to compare 1500 dimensional vectors, and there's no neat key to sort by. So it falls back to brute force, checking your query against every single vector one by one. That works for a few thousand rows, but it slows to a crawl once you hit millions. A vector database is built from the ground up for a different job. Nearest neighbor search. Find the 5 closest meanings. It uses specialized indexes with names like HNSW and IVF that skip the brute force entirely. The search time grows logarithmically, not linearly, which means it scales to billions of vectors and still answers in under 100 milliseconds. Same idea of storing data, completely different engine underneath. Let's open up that engine because this is the clever bit, the speed trick. The problem is simple. Checking every vector is just too slow at scale. So vector databases use what's called approximate nearest neighbor search, or ANN. The word approximate is the key. We trade a tiny, usually unnoticeable bit of accuracy in exchange for an enormous gain in speed. The most popular approach is called HNSW, and the easiest way to picture it is a graph built in layers. At the very top, layer 2, the graph is sparse, just a few nodes connected by long hops across the space. The middle layer is denser, and the bottom layer, layer 0, contains every single node. A search starts at the top, taking big jumps to get into the right neighborhood fast. Then it drops down a layer and refines, then drops again and refines further, zooming in until it lands on the closest neighbors. Starts pass, zoom in layer by layer. HNSW is not the only option. There's IVF, which clusters vectors into buckets and only searches the nearest ones. And there's product quantization, which compresses vectors to slash memory, sometimes by as much as 40 times at scale. You don't need to implement this yourself, but knowing the names help you read the docs and choose wisely. Speaking of choosing wisely, let's talk performance because this is where people love to argue. This chart shows approximate P99 query latency on a corpus of around 100 million vectors. And remember, lower is better. You can see the Rust native engines tend to lead on raw speed with quadrant at the front of this particular pack. Pinecone, the fully managed option, trades a little latency for convenience. But here's the honest takeaway. And please remember this, benchmarks shift constantly. The numbers you see today may be different next quarter. Under about 10 million vectors, almost any of this is fast enough. You won't feel the difference. Speed really only becomes decisive for live user facing search and for AI agents. So the golden rule, always test on your own data with your own workload. Vendor benchmarks are a starting point, never the final word. So who are the players? Here's the landscape as it stands in 2026. Pinecone is the managed category leader. Fully serverless, zero operations, scales to billions of vectors. The trade-offs is a premium price. Quadrant is the open source speed king, written in Rust with arguably the best free tier and excellent filtering, which makes it favorite of AI agents. Vivite is the hybrid search companion with built-in vectorization modules, so you can hand it raw text and a GraphQL API. Milvus and its managed cousin Zillies is the billion-scale enterprise workhorse with GPU acceleration for the most demanding workloads. Chroma is the developer's friend. It runs right inside your Python process, making it the fastest way to prototype a RAG app. And PG Vector isn't a separate database at all. It's an extension for Postgres. If you already run Postgres, you can keep your vectors right alongside with your relational data, which has quietly made it the default choice for a huge number of teams. Now, that landscape really splits along one big decision: managed or self hosted. Go managed with something like Pinecore or Zillies, and you get infrastructure to run, predictable performance with service guarantees, and the fastest possible path to production. The catch: cost tends to compound as you scale up. Go self hosted with Quadrant or Milvis, and you get full control, no vendor lock in, open source flexibility, and it's far cheaper at large scale. The catch there, you now own the operations, the monitoring, and the uptime. Let me make this practical with a quick decision guide. Just prototyping, reach for Chroma or PG Vector. Need the lowest possible latency? Look hard at Quadrant. Extremely cost conscious at scale? Self-host Quadrant or Milvus. And if you simply want zero operations and a credit card, Pinecone. There's no single best answer. Only the best fit for your scale, your team, and your budget. Now let's make this real. What can you actually build with these things? The headline use case is RAG chatbots. That's retrieval augmented generation. You ground a large language model in your own documents, which dramatically cuts hallucinations and lets it answer with real sources. Then there's semantic search, searching by intent across your docs, your code base, your support tickets, not just keywords. There's AI agent memory, giving autonomous agents long-term recall of past interactions and facts. There's multimodal search, finding images from a text description or songs that sound like a sample you give it. There are recommendations, the more like this you see on products, articles, music, and video. And there's anomaly detection and deduplication, spotting outliers and near duplicate content just by measuring vector distance. One technology and enormous range of applications. Before we wrap up, one best practice that has basically become mandatory in the 2026: hybrid search. Here's the problem: pure vector search is brilliant at meaning, but it can fumble exact terms, things like product IDs, specific names, or version numbers. The fix is to combine two approaches. One side, dense vectors capturing semantic meaning, catching synonyms, paraphrases, and intent. On the other, keyword search, often using an algorithm called BM25 for lexical precision, nailing exact matches on proper nouns and codes. You blend them together, usually with a technique called reciprocal rank fusion, into one clean rank list. Why does this matter so much? Picture an AI agent searching your support docs. It needs the idea reset password and the exact token error code 0x80070005. Vector search gets the first, keyword search gets the second. Hybrid search gives you both. And that's why it's now the default for serious production systems. Let's bring it all home with 5 things to remember. 1. Embeddings turn meaning into vectors. Models map text, images, and audio into points in a high dimensional space. 2. Closeness equals similarity. Metrics like cosine, dot product, and Euclidean measure how near two meanings are. 3. Vector databases make this fast at scale. ANN indexes like HNSW search billions of vectors in milliseconds. 4. RAG is the killer app. Grounding language models in your own data is the number one driver of adoption right now. And 5. Hybrid search wins in production. Combine semantic vectors with keyword matching for the best of the both worlds. Get those 5 and you genuinely understand vector databases. And that's it. Now you speak vector, embeddings, similarity, ANN indexes, and RAG. These are the real building blocks of modern AI search. And you know how each one fits. If this helped it click for you, do me a quick favor. Hit like so more people find it. Subscribe if you want more deep dives like this one. And drop a comment telling me which vector database you are using or thinking about using. I read them, I reply. Thank you so much for watching. This has been Gurmeet Singh, and I'll see you in the next one.